The next binary phase diagram is Peritectic phase diagram. As you can see from the example, as usual, we have metal A on the left-hand side and the composition of metal B increasing towards the right-hand side. Up there is the melting temperature of metal A, and down here is the melting point of metal B. Now you may recognize the lines. First is the liquidus line that separates the liquid phase from any other phases. Then the solvus line that you have alpha solid solution over here. The yellow line is a part of the solidus line. At point P is the peritectic point where the peritectic reaction takes place through the transformation over here, that is, the liquid phase plus one solid phase transforms into another solid phase upon cooling through the peritectic transformation. Therefore, the temperature lines over here is the peritectic temperature or Tp. And at point P, the composition down here is of course the peritectic composition. From this type of phase diagram, you can notice that in this area of liquid plus alpha solid solution is the two-phase region, and the peritectic reaction takes place once the two-phase of liquid plus alpha solid solution transform through the peritectic temperature to give one solid phase of beta solid solution over here. So once we have the beta phase in this region, the area in between the alpha phase and the beta phase is of course alpha plus beta. And up there is the area between the liquid and the beta. Hence, this area contains two phases of liquid and beta. This type of peritectic phase diagram is typical for the system of platinum and silver. And you can see in more details over here. This type of phase diagram of peritectic might look quite complicated, but let's see about the phases and composition at alloy 1 and alloy 2. Now let's make the peritectic phase diagram of platinum and silver looking more simple like this. And first we have 100% of platinum on your left hand side and the composition of silver going up towards your right hand side, reaching 100% over here, and this is on the weight basis. Up there is the melting point of platinum, and down here is the melting point of silver. Over here is the liquid phase beyond the liquidus temperature. The first solid solution is alpha, and that makes the area in between the alpha and the liquid is liquid plus alpha as the two-phase region. Over here is another solid solution phase, which is beta phase. That makes this area contain liquid and beta. And the last two-phase region over here is alpha plus beta. Now let's consider the composition of alloy 1, which is at 42.4 weight percent of silver. First, considering the alloy 1 composition at the temperature at point A, that is all in liquid. By reducing the temperature crossing the liquid phase into the two-phase region at point B, now we have the alpha phase and the liquid stay together, and the composition of the liquid phase and the alpha phase can be found by drawing a tie line over here. To find the composition of the liquid phase, you go to the right. Now here we have 55 weight percent of silver. And then go to the left to find out the composition of the alpha phase, which is at 7 weight percent of silver. And if you want to calculate the weight fractions of liquid and alpha, you can do so by taking the river rule. And by lowering down the temperature even more, we have more and more alpha phase replacing the liquid phase just before reaching the peritectic temperature. And once approaching the peritectic temperature at point C, for the equilibrium condition, the liquid and the alpha phase over here can't stay any longer. They have to transform into beta phase as the one single phase. And so at this point, we have just one single phase of the beta solid solution. And for platinum and silver system, the peritectic temperature takes place at 1186 Celsius. The composition of the liquid phase prior to peritectic transformation is at 66.3 weight percent of silver, whereas the composition of the alpha phase solid solution prior to peritectic transformation is at 10.5 weight percent of silver. And once transformed into beta solid solution, The composition of the beta phase is at 42.4 weight% of silver. Now let's find out what happened to the phases that is at the composition of 60 weight% of silver of the alloy 2 composition, and for the temperature at point D. We now in the two-phase region of liquid and beta phase. And so we have the liquid phase surrounding the beta phase solid solution. And by drawing a tie line over here, composition of the liquid phase is at 77 weight% of silver, and the composition of the beta phase is at 48 weight% of silver. Now let me explain a little bit more about how the peritectic composition has been formed through the peritectic temperature on very slow cooling, approaching the equilibrium condition. As you can see from the picture over here, we're starting from the two-phase region of liquid surrounding the alpha solid solution. Upon very slow cooling, the beta phase formed progressively surrounding the primary alpha phase. And with decreasing temperature, all has transformed into the beta phase at the end of peritectic reaction. And hence we have the beta phase solid solution as one phase after finishing the peritectic reaction. And for the last type of binary phase diagram, here we have the monotectic type of copper and lead system. As you can see from the phase diagram over here, we're starting at 100% of copper right here, and 100% of lead on the right based on the weight%. Here is the melting point of copper at 1084.5 Celsius. And down here is the melting point of lead, which is 327.5 Celsius. At the composition very close to pure copper, we have a very small area of alpha solid solution. And same here, at the right end, we have a very small area of beta solid solution at the composition of 99.94% of lead. And in the system, we have two types of liquids, which are liquid 1 and liquid 2. These two liquids are immiscible. That means they are completely insoluble in each other. The monotectic reaction takes place at the composition of 36 weight% of lead and at the temperature of 955 Celsius. Through the equation of the type, liquid 1 transforms into one solid phase plus another type of liquid that is insoluble to the previous one. Upon cooling, passing through the monotectic reaction in the equilibrium condition. So let's find all the phases in the two-phase regions. First over here we have alpha plus liquid 1. On the opposite side we have liquid 1 plus liquid 2. The area down here in the middle below the monotectic temperature where the liquid 1 transforms into alpha and liquid 2. And you can find the composition of alpha to the left and composition of liquid 2 to the right. And finally, down here, at the temperature of 326 Celsius, the eutectic reaction takes place, where the liquid 2 transforms into alpha plus beta. At last, for topic 5.2, phase diagrams for intermediate phases and intermetallic compounds. The picture on your right-hand side shows an example of the intermetallic compounds phase diagram. Assume we have metal A and metal B mixing in various composition. The intermediate phases are formed by two metals give intermetallic compounds which is stoichiometric, and that is having the distinct chemical formula, and that stoichiometric compound is AB2, as you can see over here on the phase diagram. As usual, you have the liquid over here at high temperature. So the area over here to the right you have metal A plus liquid. And now you can recognize this is the eutectic point where liquid becomes A plus AB2 down here. And therefore towards the right of the eutectic we have AB2 plus liquid. Another eutectic reaction is right there when the liquid transforms to AB2 plus B once passing the eutectic temperature. Then the area to the left of the eutectic we have AB2 plus liquid, and to the right of the eutectic we have B plus liquid. And at the composition of AB2, once we increase the temperature, the melting of this compound is said to be congruent melting. And that is, the congruent melting occurs during melting of a compound when the composition of the liquid that forms is the same as the composition of the solid. So according to this type of phase diagram, we have the congruent melting over here because the melting of AB2 compound has the same composition of the liquid that forms. Now let's consider in another type of compound melting. It is the incongruent melting occurs when a solid substance does not melt uniformly. So instead, a new solid of different composition forms during melting. And you can see from the example of this phase diagram. When we mix metal X and metal Y together, and then we have the intermetallic compound of XY2. XY2 compound is stoichiometric that has distinct chemical formula. And then towards its melting up to high temperature, this compound does not melt uniformly and have different composition that forms during melting. So it's said to be incongruent melting right here for the XY2 compound. Now let's see for the real example for titanium and nickel system. Right here on the left, we have titanium at 100%. Toward the right hand side, we have increasing nickel in weight percent. Up to here, we have 100% of nickel. Then on the y-axis, we have the melting temperature of titanium at 1670 Celsius. And for the nickel, we have 1455 Celsius over here. And when we look at this phase diagram, we can see that many phase transformation reactions taking place once we're adding up more nickel. And if we start from the liquid area up here, we still have the liquidous line over here. And you may recognize the eutectic reaction taking place at 942 Celsius at the composition of 27.9% of nickel. Another example for eutectic reaction is right here at 65.7% of nickel and the temperature of 1118 Celsius. And also right here when the nickel is at 86.1 and the temperature up to 1304 Celsius. The terminal solid solution phases occur at the ends of phase diagram that you can find from the left end over here, the alpha titanium solid solution. And towards the right end, we also have the solid solution phase that is rich in nickel. Now let's find out the intermediate phases and intermetallic compounds. The intermediate solution phases occur in a composition range inside the phase diagram. That is, throughout the composition range, we have the intermediate solution phases. That means apart from the terminal solid solution phases that we mentioned earlier, and there are also stoichiometric intermetallic compounds such as titanium to nickel over here and titanium nickel right there. And towards the nickel end, we have titanium nickel 3 compound. And the three intermetallics experience congruent melting. In summary, there are many phase transformation reactions for metallic materials. First, the eutectic reaction that the liquid transforms into alpha plus beta open cooling, and the reaction is in the opposite direction open heating. On your left-hand side showing the phase diagram characteristic, that is, the liquid phase transforms into alpha and beta once passing through the eutectic temperature. Next is the eutectoid reaction that I have mentioned earlier. For the eutectoid reaction, it is similar to the eutectic reaction, apart from we having one solid phase over here. For example, the alpha solid solution transformed into two solid phases that are now beta and gamma solid solution, open cooling. And the phase diagram characteristic is here, starting from alpha solid solution transformed into beta and gamma. And therefore the phase diagram characteristic starting from alpha transformed to beta and gamma of the eutectoid reaction. The third reaction is the monotectic reaction that we have liquid 1 transformed into alpha plus liquid 2. And the phase diagram characteristic is over here. We have the first liquid transformed into alpha and liquid 2 of the monotectic reaction. The fourth one is peritectic reaction that we have alpha plus liquid transformed into one solid phase, which is the beta phase now. And now the phase diagram characteristics looks different, that we have the liquid plus alpha transformed into beta phase once experiencing peritectic transformation. And the last reaction is the peritectoid that is similar to peritectic. Apart from we have two solid phases transform into one solid phase after cooling. And over here the phase diagram characteristic. We have two solid phases, alpha and beta, transform into one solid phase, which is gamma, after passing through peritectoid reaction. And you may see that the eutectic and eutectoid are different. The eutectoid concerns no liquid, and also the peritectoid concerns no liquid as well.